Ladies and gentlemen, thank you for checking your cell phones once more, making sure they're all off this afternoon. Our next talk is called The Close Binary Fraction, a Bayesian Analysis of SDSS M-Dwarf Spectra, and it's going to be presented to us by Ben Clark from Penn Manor High School in Millersville, Pennsylvania. Ben?
Good afternoon. My name is Benjamin Clark, and I'm here today to present my research on the close binary fraction, a Bayesian analysis of SDSS M-Dwarf spectra. There are over 100 billion stars in the Milky Way galaxy alone, and orders of magnitude more in the observable universe. While we have a firm understanding of the processes that occur within these stars, star formation remains one of the major open questions in astrophysics today. Several theories of star formation have been proposed, but observational data is needed to determine which, if any, of these theories are correct. Now, binary stars are key forms of observational data, as it's possible to determine observationally how common they are and their properties, and these can then be compared to the theory's predictions. Several previous investigations have attempted to determine the binary fraction in closed binary fraction for just this reason. However, in order to achieve the high signal noise and high resolution needed for high radial velocity precision, they've used some of the largest telescopes in the world, such as the Hubble Space Telescope and the Keck Telescope. However, due to the difficulty of being granted large amounts of observational time on these telescopes, they've been limited to very small samples, which in turn has decreased the precision with which they can determine the binary fraction, closed binary fraction. A means to overcome this difficulty would significantly help to advance research in star formation. Thus, the goals of my research are: 1, to develop a means to analyze an extremely large, low resolution, and signal noise data set in order to determine the closed binary fraction of M-dwarfs; 2, to conduct this analysis using data from the longitudinal sky survey and determine the closed binary fraction of M-dwarfs; and 3, consider the implications of this result to star formation theories. The longitudinal sky survey, more commonly known as the SDSS, was a major international collaboration that used a 2.5-meter telescope located at Apache Point Observatory, New Mexico, to conduct imaging and spectroscopy over a full one-quarter of the sky. The final data release contains multiple spectroscopic exposures of over 1.6 million objects, of which 464,261 are stars. Of these, 51,193 were identified as M-dwarfs by Knapp et al. 2010. Now, while this data set is incredibly large, due to the limitations imposed by the telescope and CC detectors used, it's significantly lower resolution and signal noise than that used in previous investigations of the binary fraction and closed binary fraction. Now, starting from this list of 51,193 M-dwarfs, I applied 2 cuts to the data set. I wrote objects that were too faint and too dim based on the limitations of the CCD detectors that were used by the SDSS. I then divided the data set into a control sample and an experimental sample. The control sample consisted of objects which were observed over a period of 0 to 4 hours, as these objects will not exhibit significant radial velocity variations, even if they are in fact binary stars. Thus, using this data set, we can determine the accuracy of the calculated radial velocity values. On the other hand, the experimental sample consists of objects observed over a period of 2 days to 30 days. These objects will exhibit significant radial velocity variation if they are in fact binary stars. The control and experimental samples contain 30,076 and 6,787 objects respectively. Now then, for each observation of each of these objects, I calculated the radial velocity, the velocity in the line of sight. Now, due to the star's radial velocity, its stellar spectrum undergoes a Doppler shift. That's by comparing the observed stellar spectrum to a template spectrum, which has not been Doppler shifted. It's possible to determine the magnitude of the Doppler shift and thus the radial velocity. Now, each object was fit to 11 templates, 1 for each spectral class from M0 to L0, using chi-squared fitting, and then the best fit template was used. The graphs shown here show template spectra for an M6 star. Wavelength is on the x-axis and flux is on the y-axis, and then a chi-squared versus radial velocity plot for one particular observation, just an example. And then after calculating these radial velocity values, I applied several additional cuts to the data set. I removed any observations with signal noise less than 10, or among the 10% of observations with the highest chi-squared, as both of these factors decrease the radial velocity precision that can be attained. I then removed any objects with less than 3 observations remaining. Now, after these cuts, 7,081 objects remain in the control sample, and 1,639 remain in the experimental sample. Now, I then had to devise a metric to quantify the level of radial velocity variations. This has not been needed in previous research, as due to the large number of observations they have of each object and the high radial velocity precision of these values, they were simply able to fit radial velocity curve to the data. This is not feasible given the 3 or 4 observations which are normally taken by the SDSS and the lower precision of those values. And thus, I developed the metric X that you see here to quantify this level of radial velocity variations. And then using this metric, I carried out a Monte Carlo simulation of 10 to 7 trials using the data from the control sample to set the detection cutoff so only 1 in 10 to the 3 single stars would exceed the cutoff and erroneously be detected as binary stars. Now then, using this cutoff, I found that 22 of the 1,639 stars in the experimental sample were treated as binaries. Now then, in order to determine the close binary fraction, I had to account for two factors, the detection inefficiency and false detections. Now I did this using the techniques of Bayesian inference. Now by Bayes' theorem, we have the relationship that you see here, where n is the close binary fraction, d is the number of objects detected, and b is the relevant background information, which includes the times of the observations and the colors of the objects. Now we wish to determine p of n given d and b, and we can do that by determining p of d given n b and p of n given b. Now in order to determine p of d given n and b, I had to calculate the detection efficiency of each object, and I did that by carrying out a Monte Carlo simulation of 10 to the 5 simulated binaries. Now for each one of these simulated binaries, I inserted values for the semi-major axes, mass ratio, primary mass, longitude precession, phase, and inclination from the appropriate distributions, and then calculated the rate of velocity values that resulted, and then the criterion x that I established, and determined what fraction of those trials in which it exceeded the cutoff that I established. Now, all this analysis was carried out using code that I wrote in IDL, interactive data language. The total computation was approximately 8,000 CPU hours. Now my results. The delta RV values for the control sample had a standard deviation, or root mean square, of 4.1 kilometers a second. A histogram of these values is shown here. Now this compares very well with the values given by the SDSS of 5.5 kilometers a second at g equal 18.5 and 12 kilometers a second at g equal 19.5. Now, this distribution did have a small but large expected set of outliers. 15 of the 7,081 objects in the control sample had at least one observation with delta RV greater than 20 kilometers a second. I examined several possible explanations for this. However, all would be limited other than an error in the wavelength calibration, which would be previously unknown error in the raw data reported by the SDSS, or that the object is an exotic binary undergoing very rapid orbital motion. Further data is needed to determine which of these two is in fact the cause. Now, carrying the Bayesian analysis I described yields the posterior distribution p of n given d and b shown here. Now from this, it follows that the most likely value for the close binary fraction is 3.1%, and that the one sigma confidence interval is plus 0.6 minus 0.9%. Now there is one previous result on the close binary fraction of M-dwarfs that are Fisher and Morris in 1992. Based upon a sample of 62 objects, they determined the close binary fraction of M-dwarfs to be 1.8 plus 1.8 minus 1.8%. This is a significantly smaller sample than that used here, which contained 1,639 objects, and is a less precise determination of the close binary fraction. However, it is worthwhile, though, to note the two do agree to within their error. And then I also compared my result to previous results for the close binary fraction of L and G Spectra classes. A table of those results is shown here. Now, from looking at this, it's clear that the close binary fraction increases the function of mass. This is a new result. While it had previously been shown that the total binary fraction increased the function of mass, the same had not been shown of the closed binary fraction. Now, what are the implications of this result to star formation? Now, while comparing the specific value that I found for the closed binary fraction of M-dwarfs to theories of star formation, we require computing these theories predictions by carrying out highly involved M-body simulations, which I've not undertaken here. I have, however, examined the implication of the result that the closed binary fraction increased the function of mass to one of the primary theories of star formation. This theory predicts that stars form in small clusters, which are then broken apart by two processes, dynamical decay and dynamical destruction. Dynamical decay occurs as these small clusters are dynamically unstable, and so they fall apart, preferentially ejecting the least massive component. When dynamical destruction occurs when another object in the star formation region flies by the small cluster and breaks it apart, dynamical destruction by itself would predict that the closed binary fraction should be constant function of mass. But since I concluded that it increases the function of mass, it follows that dynamical decay, or some other yet unknown process, must play an important role in star formation. In conclusion, I have developed a means to analyze an extremely large, low-resolution, and signal-noise data set in order to determine the closed binary fraction of M-dwarfs, determine the closed binary fraction of M-dwarfs more precisely than previous research, consider the implications of star formation, and demonstrate the possible use of large-scale survey data to improve the precision with which the binary fraction and closed binary fraction are known. Now, this analysis determined the closed binary fraction of M-dwarfs using data for 51,193 M-dwarfs which were observed by the SDSS. However, the SDSS observed a total of 4,261 stars, which is approximately 410,000 stars of various spectral classes which remain to be examined. Carrying out analysis similar to that which I have done here on these stars would be able to yield values for the closed binary fraction of stars of these spectral classes, which would further support the conclusion found here that the closed binary fraction increases the function of mass. Now, future surveys would offer the possibility of further improvements in the precision with which the binary fraction and closed binary fraction are known. However, there are no large-scale spectroscopic surveys which will match the size of the SDSS, which we're planning within the next decade, so that the Princeton the SDSS is the best set with which to work. It'd also be worthwhile to carry out observations for the 15 objects in the control sample, which I found to have very large delta RV values. If these objects turn out to be exotic binaries, rather than simply due to an error in the wavelength calibration, they would be very interesting objects to study as they are very rare. I would like to thank my mentor, Dr. Cullen of Princeton University, for all the advice he supplied to this research. I'd like to thank Dr. Jillian Knapp, Courtney Dressing, and Dr. Craig Loomis for being willing to share their knowledge, and parents for their support. I'd also like to acknowledge the many members of the STS collaboration. Without his hard work, this research would not have been possible. These are my references. Thank you very much for listening.